Hello, welcome to Maths with EJD. In the previous video, I began to talk about Hungarian method for solving assignment problems. And I also gave an example of four workers with four tasks, and we got the optimal solution with the associated cost. In this video, I'll be looking at a specific problem, which is a project assignment problem, where we have uh, four contractors. We have four contractors, and we have four projects that any of the contractors can handle any of the four projects. And then, but we are more interested in the completion time of the matrix. So we have a completion time matrix. So completion time is of essence here. So, and then we have this associated completion time matrix. So you have project one, project two, project three, project four, and then you have uh, you have contractor one, contractor two, contractor three, and contractor four. And then the completion time matrix is such that contractor one does project one in 19 weeks, and then contractor one project two, 13 weeks, contractor one project three, 17 weeks, contractor one project four is in 15 weeks. And then we have the rest like that 14, 18, 12, 18. Then we have 21, 18, 15, and 20. Then we have 14, 19, 18, and 17, like this. So that's what we have right there. So of course, the objective is so we want to um assign assign a project, assign a project to each contractor, or should I say, assign a unique project to a unique contractor, to a unique contractor, to a unique contractor in such a way, in such a way that completion time, completion time is minimized. Completion time is minimized. Okay, that's what we have to do. All right, so since we have that, now let's just go straight to the solution using the Hungarian method. So first of all, you have 23, 19, 18, 33, like that. Oh, sorry. I think I'm doing another one. So this is 19, right? 19, 13, and all that. So we have 19, 13, 17, 15, and then we have 14, we have 18, 12, 18, then 21, 21, 18, 15, 20, then we have 14, 19, 18, and 17. So this is the uh, time completion time matrix. So like we already have learned, right? The first step we have to take here is to do the row 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 minimum subtraction, row minimum subtraction. Okay, row minimum subtraction. So the row minimum subtraction means that you identify the smallest value in each row. In row one is 13, in row two it's 12, in row three it's 15, in row four it's 14. So you subtract each of the smallest values from their corresponding rows. So 19 minus 13 is 6. 13 minus 13 is 0. 17 minus 13 is 4. 15 minus 13 is 2. Okay. And for the next row now, you have 12. This 12 now. So 14 minus 12 is 2. 18 minus 12 is 6. 12 minus 12 is 0. Then 18 minus 12 is 6. Then coming to the third row now, you have 21 minus 15, that is 6. Then 18 minus 15, that's 3. 15 minus 15 is 0. And then you have 20 minus 15, which is 5. Then the last row is 14. So 14 minus 14 is 0. 19 minus 14 is 5. 18 minus 14 is 4. Then 17 minus 14 is 3. So this is the next thing you have. Okay. So that is the row minimum subtraction. The next thing you need to do is to now find you find the column minimum subtraction. Okay. So you have So for column minimum subtraction now, column minimum subtraction. So here now, you need to find out in each column which number is the smallest. So 0 is the smallest here, 0 is the smallest here, 0 is the smallest here. In fact, you have two zeros that are smallest. Wherever you have 0 as the smallest, it means that column is not going to change. But here we have 2, it means that is going to change. So the next matrix we're going to have now is that is okay. You are going to have 6 2 6 0, and then you have 0 6 3 5 0 6 3 5. Then you have 4 0 0 4 4 0 0 4, and lastly we have 0 4 3 1. That's 2 minus 2. 2 minus 2 is 0. 6 minus 2 is 4. 5 minus 2 is 3. 3 minus 3, I mean 3 minus 2 is 1. So we have 0 4 3 1. So that's the next step. So don't forget, this is step 1. This is step 2. Then the next thing we have to do now is to check for optimality. Okay, so we check for optimality. Check for optimality. So checking for optimality means you're going to cover all the zeros with the minimum number of lines that can cover them. So it means you have 6 2 6 0 0 6 3 5. Then we have 4 0 0 4, and then we have 0 4 3 1. Okay, so you want to cross out the lines in such a way that you want to use the minimum number of lines. So, you can actually say cross this, cross this, cross this, cross this. That is 4 lines, and it will be like optimal. But is that the best you can do? You can also think about doing this 1, 2, 3, 4. That will also cross out the zeros, right? But is that the optimal thing you can do? If you check properly, you discover that there are better ways you can do this. For instance, you can cross this, and cross this. So you see, you have 3 lines covering all the 5 lines. And in that case now, since you have 3 lines, you can actually have 3 lines. I don't think you can do better than that, right? You can't do better than that. So 3 lines is not equal to number of rows. It's not equal to number of rows. Of course, number of rows is equal to number of columns. So in that case, you can say no optimal solution yet, no optimal solution, no optimality yet, no optimality yet. So so that's our check for optimality. And then if there's no optimality yet, the next thing you have to do is to modify the matrix. Okay. So the next step now, this is step 3. So step 4 now is to modify, modify, modify matrix. And how do you modify the matrix? From the law, you are going to check for the smallest number in this matrix. The smallest number here is 1. So, and what do you do with that smallest number? First, the number one thing is you add that smallest number, which is 1, add it to the intersection elements. So add that one to the intersection elements. That's the first thing you're going to do. So, and what are the intersection elements? So this 6 and this 4, they are like the intersection elements. You're going to add 1 to them. And the other thing you're going to do is to subtract. So subtract the same 1, subtract 1 from uncovered, subtract 1 from uncovered elements. So every element that is not covered, 6 4 3 3 1 5, they are not covered. All right, you are going to subtract 1 from every uncovered element. Then the last thing you're going to do is what are you going to do with the ones that are not at intersection? So you're just simply going to leave all other covered elements, leave all other covered elements the way they are. All right. So that means that you're going to add, so you're going to have something like this. Add 2 to 6. Sorry, add 1, right? It's 1 you're adding. So the new matrix becomes 7, 0, 5, 0. Okay. And then, of course, all these other ones remains the same because they were not covered. So, I mean, they were covered with just one line, not at intersection. So you have 7, 2, 6, 0. And then now you subtract 1 from all the 6, 3, 5. So it becomes 5, 2, 4. And then all these ones remain the way they are, 0, 0, 4. And then all these ones also, you're subtracting 1 from 4, 3, 1. That'll be 3, 2, and 0. So this is the new matrix you have after modifying the matrix. So again, now, you also want to check for optimality, okay? So again, you check for optimality. So that's step 3 now. Okay, step 4. So we have step 5. Again, you check for optimality. For check for optimality. So let's see again. So if you want to check for optimality, so again, you can just write this out. You have 7260, 7260. You have 0524. You have 5004. And then you have 0320, like this. So to check for optimality again, it means you look for the minimum number of lines with which you can cover the zeros. So like we did before, right? We can still say, we can say 1, 2, 3, 4. But is that the minimum you can have? You can also say, you can also do 1, 2, 3, 4. But is that the minimum you can have? No. If you look properly, we can have 1, we can have 2, and then we can have 3. All right? So what happens? We still have 3 lines. We can have 3 lines, and that is not equal to number of rows. It's not equal to number of rows, which of course, number of rows is equal to number of columns. So because of that, so we say no optimality again, no optimality yet. Okay. And what do we do next? We modify the matrix. So modify. So step 6 now, you modify the matrix again. Modify the matrix. Modify matrix. Okay. Modify matrix, which we like what we did before. So you modify matrix. How do you modify the matrix? Check around the smallest number you have anywhere. So you can see the smallest number here is 2. We have 2. That's the smallest number. So you have 2. So again, what are you going to do? You're going to add 2. So 1, add 2 to the intersection elements. Add 2 to the intersection elements like we did before. Okay. So that means you're going to add 2 to this 5. Don't forget this was 5, right? So add 2 to that 5 and then add 2 to this 4. Then having done that, you're going to subtract. So this is plus 2, this is plus 2. Now you're going to subtract 2 from everything that is not covered. Minus 2, minus 2, minus 2, minus 2. So every other thing remains the way they are, okay? So that means that, so of course, subtract 2 from uncovered elements, So that's all you need to do. Every other thing, you leave it just the way it is. So let's do that. So 7 plus 2. So not 7 plus 2 now. It's 5 plus 2. So here now we have 7, 0, 7, 0. And then we have 0, 3, 0, 1. And we have 4, 0, 0, 0. And then we have 0, 4, 6, 0. Because, 5 plus 2 is 7. That's what we have down there. Then 4 plus 2 is 6. 3 minus 2 is 1. 2 minus 2 is 0. Then we have 5 minus 2, all that. So we have 0, 3, 4, 1. I mean 0, 3, 4, 0, like that. And this is what we have now. So again, you want to check for optimality. You We want to check for optimality. In this case now, whatever you do, anyhow you try, okay, maybe I should just say check for optimality. That's step 7 now. Step 7, check for optimality. So step 7, check optimality. Check optimality. So in an exam situation, you don't have to keep drawing this. You can even do everything in just by just writing two matrices. But here I have all the time to explain. So you have 7050, you have 2503, you have 6202, and then you have 044. Oh, sorry. Sorry. I should be showing you the latest one. So I have 7070, then I have 0301, then I have 4000, and I have 0460. I want to check for optimality, right? So 7070, 0301, 4000, 0460. So we want to check for optimality. So let's try. In what ways can we try? So 1, 2, 3, 4. We have covered all the zeros. That's one way. 1, 2, 3, 4. We have also covered all the zeros. That's another way. Is there any other thing we can try? Can we try 1, 2? Can we try 1, 2? Okay. 3, 4. In fact, this is 5. So of course we have 5 now. So that, of course, 5 is more than 4. So is there any possibility of having less than 4 ways of covering this? No way, I think. So the worst we can do, the least number of rows can be 1, 2, 3, 4, either horizontally or vertically. So in that case now, we can say that 4 lines, right? We have 4 lines, and 4 lines is equal to 4 lines is equal to 4 is equal to what do you do is so 3 lines, right? So here we say 4 lines is equal to number of rows or number of columns, as you may wish, number of rows, which is the same thing as number of columns. So in this case, optimality is reached. Optimality is reached because we can't have less than 4 lines crossing the zeros, covering the zeros. So what do we do next? Then we go for optimal solution. So optimal solution. So what would the optimal solution look like? Let's see that. The optimal solution, okay. The optimal solution is going to be we have to use our discretion now to get the optimal solution. This is step 8 now. So from what we have, 7070, then 0301, then 4000, and then 0460. And then what are we doing? We have contractor 1, contractor 2, contractor 3, contractor 4, project 1, project 2, project 3, and project 4. That's where we started from. So how do we do this? So we need discretion. Like I said, we need discretion here. Okay. So we have seen that we can actually do vertical or horizontal. So we have 1, 2, 3, 4, or vertically 1, 2, 3, 4. So how are we going to choose how to assign the problem? Now, for contractor 1, right? Contractor 1 has 2 options. Contractor 1 can take project 2 or project 4. Okay. Now, so we can just let's just assign contractor 1 this first project. Okay. Of course, project 2 can be assigned to contractor 1 or contractor 2. But once you assign one project, then automatically it means that contractor 1 can no longer handle this project because one person has to just take one project. Okay. So the next thing we want to do now is to see that contractor 2 has options to take project 1 or project 3. Okay. So we can just assign contractor 2 to project 1. And that means that contractor 2 can no longer handle this third project. Okay. Now we go to contractor 3. Now contractor 3, of course, cannot handle project 2 because project 2 is already assigned. Project 2 is already assigned to contractor 1. So contractor 2 cannot take that. Then project 3 is already assigned to contractor. So contractor, I mean project contractor 3 can also take project 3 because project 3 has contractor 2 has taken project. Oh, okay. Sorry. That's not true. Okay, of course, contractor 2 cannot take project 3 again. So project 3 has to go to, so project 3 has to go to contractor 3 because project 2 is already gone. So this is gone, okay? So contractor 3 has to take project 3. And of course, contractor 3 is already has something. So this can also go. So and then since project 1 has been assigned, contractor 4 cannot take this. So that contractor 4 can now take this. So that would now be the optimal assignment we have now. So that's the optimal assignment we have. So since we are talking about the optimal solution, so we can just say, so the optimal assignment, the optimal project assignment, the optimal project assignment is such that optimal project assignment is such that contractor 1 takes project 2, okay? Contractor 1 takes project 2, and the cost in the original table, I mean, the time duration is 13 weeks from the original table, if you remember. So it's 13 weeks. Contractor 1, project 2, that's 13 weeks. Then you also see contractor 2 takes project 1, 14 weeks. Contractor 3 takes project 3, 15 weeks. Contractor 4 takes project 4, 17 weeks. That's all we are going to have, right? So we do that. So contractor 1, project 2, 13 weeks. Contractor 2, project 1, 14 weeks. Contractor 3, project 3, that is 15 weeks. Then contractor 4, project 4, that is 17 weeks. Okay, so we can just say duration, total duration now, based on this optimal assignment, the total duration will just be 59 weeks. Okay, the total duration is 59 weeks. Okay. So that is how it's going to be. Of course, how do we get to 59 weeks? 13 plus 14 is 27. 27 plus 15 is 42. Then 42 plus 17 is 59. So the optimal assignment is such that all the projects are completed within 59 weeks, like that. Okay, that's the minimum we can have. So in the next video, I'll be talking about a matchmaking assignment problem. So assigning unique men to unique women for dating or for marriage or something. So maybe that kind of thing can be useful for a dating app. All right. So if you have not subscribed to the channel, there's so much more coming your way. So you want to do that right away. And then, of course, hit the notification bell so you can always get alerted each time a new video is released. Then let me know, comment. Let me know if you want me to teach a topic or solve a problem, and like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.